TV? Okay, cool. That would have been really awkward if it didn't. Right, gentlemen, are we excited? Okay, cool. Me too. Me too. So excited and I just can't hide it. Hopefully the screenshot from the meme today is a screenshot from Untitled Goose Game, which is literally just a game about you being a dick. It's great. If you ever have the opportunity, it has co-op. And it is fun. Literally just be a nuisance to this little village. It's great. What's that? Oh, you know, locking the gardener out of his own garden. It's a good start. Yeah. So today, gonna review the geometric figures we covered last time. Then we'll move on to the Pythagorean theorem. We'll call it good on the basics of geometric figures from there, and we'll look at charts and tables before going on to graphic. It'll be fun. So, rectangles, they exist. They're squarish, but not really. The difference between area and perimeter is that area is a measure of the surface of the shape, where perimeter is the measurement of distance around the shape. So on the left, it's filled in, area. On the right, it's not, it's the border, not area. Perimeter, it exists. Useful things, we got formulas. These ones are pretty easy to put together on your own, but if you don't have that, you know, handy in your brain, you can always just roll off of these. Area of a rectangle is always the length multiplied by the width. That always gives you square units. So if it's inches by inches, it's square inches. Then perimeter is, since the opposite sides of a rectangle are equal to each other, you have twice the length plus twice the width. You could always just say length plus width plus length plus width, or however you want to do it. But the usefulness of this formula comes in handy pretty regularly when you're doing some more advanced algebra. So this formula is pretty useful. So we do, of course, have some rectangle problems, both of which are dealing with Kevin Bacon. Because why not? Kevin Bacon is building a rectangular garden in his backyard with his mind. Telekinesis. What's that, telekinesis? The length of the garden is 12 feet and the width is 8 feet. One of the lengths will be along the wall of the house and will not need fencing. What's the perimeter of the garden and how much fence will he need to fence? And what is the area of the garden? Oh my God, look at this beautiful little figure. Like painting a wonderful tapestry. Like she's saying about Pocahontas, I'm painting with all the colors of the wind. You know, it's dusty outside and your wind is black like this. So we have some fencing and it's around a rectangular garden, 8 by 12. So 12 on both sides, 8 on both sides here. So we're looking for how much fencing we're going to need for the perimeter, and we're looking for the area. So If we're looking for initially the perimeter, our formula for that is twice the length plus twice width. Yay. We can fill in our blanks. 12 for the length, 8 for the width. Do our multiplication. And add them together. Isn't it beautiful? So beautiful. So we know our perimeter, the perimeter of our garden is 40 feet. But how much fencing do we need? That's where the fact that this is a word problem comes in handy, because you'd think they would be the same answer. But this is saying, hey, this is fencing in against a wall, so we don't need that length. So you would just have the 40 feet minus 12, or you could say length plus twice the width, however it is you want to do it. That'll be 28 feet of fencing. That's 2 out of 3 of the answers. Last one was asking for the area. Area of a rectangle, length times width. So in our case, we just have 8 by 12. Is what, 96? What's that? We had feet times feet, so it's gonna be square feet. You feel like you've learned something today. This is the most enriching experience of your day so far. Yeah, no. Oh, work's overrated. I didn't have that today.
Tomorrow's payday, so it'll probably feel different than mine.
Tomorrow's not payday for me. Payday was last week. That lasted about an hour. It's already gone. Okay, number 2. The Bacon Meister wants to cover the floor of his rectangular room with the most violently red shag carpet. The length of the room is 18 feet and the width is 12 feet. Feet, 12 feet, definitely not the scale or totally wrong. What is the area of the room? How much carpet does he need to buy? And it says the cost is going to be $14 per square foot. And the installation is a flat fee of $400 plus $3 per square foot. What will be the cost? That's a pretty solid problem, right? It's decent, it'll do. Now, a nice thing on a problem like this, it's asking for the area and it's asking how much carpet you need. This isn't like the last problem where we had to chop off one side of this thing. The area is going to be how much carpet we need. So luckily, the answers to those guys are equal to each other. We can just say, yay, I have this much square footage. Likewise, if we're looking for the cost, we know that we have the base cost of the carpeting and then the install price, and we can just put those together as well, right? Because whatever those are added together is going to be our total cost. So when we get to it, we can just go ahead and slap that on there, right? Now, normally this is the sort of thing I would, create a formula for, but since we're going to immediately work out to find the square footage right away, we're not gonna need one. On a problem like this, if you find yourself doing the same, like, say you're working for this carpet company and you're trying to create a formula for, being able to just plug in a certain size and get out a payment. That's the sort of thing I would use a formula for on this. But again, I'm not going to need one because we're only dealing with one. So the area is going to be the length times the width. So 18 times 12. It's a big enough number that I don't know what the heck it is. 216. So we had feet by feet, so this is square feet. Okay. Now we know how much square footage we have. So we can put together a general idea here. So we know that it costs a base amount of 400 bucks. So whatever our cost is per square foot is going to be 400 added on top of it. If the carpet is $14 per square foot, and then installing each piece of carpet, because that's a jerk move, but installing that is $3 per square foot. That would give you 17 per square foot total, right? You can have 17 multiplied onto our square footage. Whatever this is, it's going to be our cost. 216 times 17 plus 400. Get 4,072 for the most violently red shag carpet you ever seen. Got to be the kind of color where you would look at it and you would say, you know what? I thought I knew what color red was in this moment. Redefine the color for me. Like when you see, I haven't seen it in person, but I think it's called like Vanta Black or something, where it's just a pure black color that somebody literally owns. They apparently own the color. But they own the color, and if you paint something in this, it absorbs so much light that it almost looks like there's nothing there. Which would be really fun to paint a car with. An electric car where you disable all the noises inside, so it runs around silently. And that would be horribly illegal. It would blend into everything. It'd be great. Any questions on rectangles? Perhaps any questions on the shape of them? They're rectangular. We next covered some triangles. So triangles, we're pretty used to them. They're shapes with three sides. Main thing is that there's 4 different types that we tend to work with. Equilateral triangles have, well, the lateral means lines, so equal lines. Each of the sides are equal, and that takes your total of 180 degrees, chops it into 3. So all of the angles inside of an equilateral triangle are always 60 degrees. The other options are, we have a isosceles triangle. That one's close. It's got 2 equal sides. If it has 2 equal sides, then it would have 2 equal angles. And then the other side is just kind of whatever. Think of like an oddly triangular shaped building. There's some weird ones in metropolitan areas. I don't know. I wouldn't want to walk around inside of a triangle. Scaling is just a fancy word for none of the sides or angles are equal. So that one's just funky looking shape. It's fine, it's a triangle, but there's nothing special about it. And then the most useful in terms of actually working things out is a right triangle. Right triangles always have 190-degree angle. So usually you'll see that represented with like a little squared off symbol instead of the usual like half circle that you would see in an angle. Past that, since all the interior angles of a triangle add up to 180 degrees, if that one's 90, that means the other two are going to be complements. They both have to add up. So the usual idea, perimeter and area, there's no fancy formula for perimeter of a triangle. You just add up all the sides. Now the area is a little trickier. It's a lot easier to picture if you have a right triangle. But if you think of like a rectangle being divided by its diagonal, it would make two right triangles. So the area of one of them would be 1/2 the length times the width. So the formula for a triangle is 1/2 base times height. Now, the reason it goes with base and height instead of length and width is because you're not guaranteed to have a right triangle. So the height is always going to be that vertex opposite from the base, straight down to the base. So the downside is if you have something trickier than a right triangle, you end up having to make right triangles solve. Now, how do we do that? Oh my God. I'm just jumping straight into geometry for the Pythagorean theorem. That way you can get to some other stuff quicker. So here we have something that relates all three sides of a triangle together. This only works with a right triangle. So if you're working with trying to find, say, the area of a triangle that isn't a right triangle, you end up having to make two separate right triangles and working them out in a really funky way. But all we need to worry about right now is that in a right triangle, the square of the length of the hypotenuse, which is the largest side, it's always straight across from the right angle as well. It's equal to the sum of the squares of the lengths of the other two sides. So you got the long side squared is equal to both of the other legs, each being squared. You add them together and there's your problem. This has a ton of different uses. You can find lengths of all kinds of different shapes this way. When you get to a certain level of playing around with geometry, sometimes you're like, yeah, I can cram a triangle in that and make it work. I could figure out the height that way. A lot of times you end up using the Pythagorean theorem when you wouldn't expect to. So solving for it, as an example, you have the legs and you're looking for the hypotenuse. You plug in, say, in this case, we have 3 and 4 for the legs. 3 squared plus 4 squared is c squared. 3 squared is 9, 4 squared is 16. Add them together and you get 25 is equal to c squared. So you always solve for that one extra term that you don't know yet. And then since it's always going to be squared in this case, you're going to end up square rooting both sides to solve for it. So the square root of 25 would be 5. Now I will point out when I covered square rooting a number, I did say that anytime you square root a number, you have to add a plus or minus, because if you square the negative, you still get the same number. That's a little different in geometry because we're talking about actual shapes, and I'm not gonna have a shape with a negative side. So we just roll with the positive option. Questions, comments? Screaming? I'm screaming, okay. Got a few examples here. So the ladder leaning against the wall forms a right triangle. Base of the ladder is 6 feet. From the wall. That makes more sense. So the base of the ladder is 6 feet away from the wall. And the height of the wall is 8 feet. What is the length of the ladder? So we got this little guy. We got a random ladder hanging out. Look at it, isn't it beautiful? But it's a ladder. Oh my goodness. I know, it's surprising I don't have an art degree. So we have that the base of the ladder is 6 feet away from the wall and that it's touching 8 feet up on the wall. We're being asked, okay, well, what is the length of that ladder? Well, since that ladder be the hypotenuse of this triangle, or trusty Pythagorean theorem, we say, okay, well, just for sticking with the variables that this gives us, we can call the ladder C. Now, it doesn't matter which leg is which, A or B, because there's both on the same side and they're both being squared and added. So it'll work out the same either way. So let's say we had 8 squared plus 6 squared equal to C squared. Multiply everything out. 8 squared can give you 64. 6 squared can give you 36. Add them together. Oh my God, we get 100 is C squared. If something squared is equal to 100, what do you think of something else? Square root both sides. Get C left over here. We get 10 over here on the left. So the length of the ladder, 10 feet. How do we feel about that? Is okay? Is it not okay? Is tolerable? We're here. We're all happy to be here. Class isn't down to 2 people quite yet. But it will be next week. I don't know which of you, but one of you won't be here because I end this class every time with 2 people. That's how it always goes. Funny thing is, I believe my replacement for teaching this class is going to be sitting in on Tuesday's class. So I'm just going to look at her and be like, well, this is what you can kind of expect by the end of your class. I am going to just take a break. I've been teaching this for 3 years. It's always been an after my job, I have another job thing. I'm tired. It's a good amount of work for a very little pay. Like, yay, you get paid 22 an hour for only class time. Like, my God, look at what, this is just what we haven't covered yet. Look at all this stuff. I wrote all this stuff in my own time. Oh my God, we still got memes. I know who she is. I have not met her.
Was it one that, you know, if she was already like looking around classes already?
I have no idea. It's possible. I mean, to be fair, I haven't gotten confirmation that that's who's taking over my class, but why else would we have another teacher randomly sitting in on classes in the last couple of weeks? Just my assumption. I feel like it was a safe one. Let's see.
Yeah.
And we're scrolling, and we're scrolling, and we're scrolling. Heather Mata. Yeah. I don't know who you are, Heather Mata, but I'm about to find out. Her name's Heather. I don't know. I'll find out, you'll find out, we'll find out. We'll find out together. Actually, most people are gonna find out before me because God knows I'm never on time for my own class. All right.
She wasn't on time last time.
No,
She was like 30 minutes late actually. So,
I mean, sitting in on a class to check things out and observe is actually, that's perfectly fine. I usually 30 minutes late. I wonder if that was my boss. Maybe. I don't know. He tends to pop in about 30 minutes in. All right, let's look at more. We like these. Let's have more fun. I want to make it hard. This isn't a good one to be difficult for the question. How could I make a difficult Pythagorean theorem question? How to be cheap. Copy. Paste. Images. Don't like it, don't like it, don't like it. What is that? That's kind of hideous. Oh, yeah, we can't do that. All right. What is that? No. What is that? No. Is there anything hideous? I don't like any of these. No. No. Well, that is actually a great question. Blah, 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 blah. I don't like any of these. Okay, cool. All right. I like that problem. We're gonna do that problem. That's an interesting one. I haven't seen a problem quite like that. I like it. Question is, does this have a right angle in it? Which is an interesting question because at this point, we haven't really played around with how to find angles. So how would you find out? All we know is a squared plus b squared is equal to c squared. But we only know this for right triangles. That's the only time it applies. It's not going to apply on, isosceles, no scalenes. It only applies to right angles. So the way that you would see if there's a right angle in this, if it's a right triangle, is to test it. You plug it into the formula and you see if it works. If it works, then it's like, okay, well, it has to be a right triangle because the formula works. If it doesn't work, then it's not a right triangle. Now, at that point, the longest side is always going to be the hypotenuse. We're going to call that C. The other two are A and B. Doesn't matter which is which. But the basic idea is we're just going to take these and plug them in, see if it works. If it works, then it's a right triangle. So we have 10 squared plus 24 squared is 26 squared. And when you're doing this sort of verification, an important thing is that you usually don't move one thing from one side to the other side. That isn't 100% set in stone, but it's just kind of a rule of thumb how things are done sort of thing. So you would have 100 plus 576 is equal to 26 squared, which is 676. Yeah. 100 plus 576 is 676. And since the left side is equal to the right side, then you say, okay, cool, it worked out. If it worked out, that means this was a right triangle. That means that my picture is kind of crappy and it would actually look closer to this, an actual right angle in there. Is it necessary to write the problem, write the triangle again? No, just there for verification. But does that make sense? Does it not make sense? Does it not make sense? Anyone mentally here right now? You are definitely here. Okay, cool. That's 1 out of 4 if you include me. All right. So, yeah, but that's a pretty good question. I like that one. Okay. Then we have number 3. Skipping number 2 because honestly, I just didn't like it. Basically, the same problem. So, number 3 says a flagpole casts a shadow that is 8 meters long. That's telling us, okay, that's probably going to be the hypotenuse, right? That's, well, that is not the hypotenuse. That's where my brain is working today. That's what happens when I'm feeling sick. My brain starts doing stupid stuff. So if the shadow is 8 meters long, that means it's literally the length of the shadow. So it's on the ground. The flagpole is perpendicular to the ground, which means that it is at a perfect right angle, giving us our right triangle. And the distance from the top of the flagpole to the end of the shadow is 10 meters. What is the height of the flagpole? So we're saying 8 meters is the length of the shadow. Distance from the top of the flagpole to the end of the shadow is 10 meters. And we're being asked what's the height of the flagpole. For the fact that it's a height, I'm just going to call it H. And when I do my this squared plus that squared is equal to this squared thing, I just need to remember, okay, these are the legs. That one's the hypotenuse. So it's going to be this squared plus that squared is equal to that squared. Damn it, this is the same triangle. So we square the 8, we get 64. We square the 10, get 100. Subtract 64 on both sides, get that h squared alone. And then we can square root both sides to get the h on its own. H is equal to, and the square root of 36 is 6. This is in meters, this is in meters, so this one is also going to be in meters. Calling it h for height can come in handy. Naming your variables correctly is a very useful thing when you get into algebra, because I will see people go with the generics at all times, X, Y, and Z, A, B, and C. And then they get to the end of a word problem and they're like, I don't actually know what this is that I have a number for. They'll get to the bottom and be like, 6, cool, 6 what? So being able to name them appropriately, H for height, D for base, that sort of thing. Seems like it's just kind of there for no reason, but it does come in handy the more complicated the problems are. Questions on Pythagorean theorem? Not bad, right? Got a couple of things squared, you just add some stuff together and square root at the end. Okay. Now, past that, we got a bunch of stuff on tables, charts, graphs, all kinds of stuff. Tables are the ones you're the most familiar with. Table of information. You just have rows and columns of data. They can be kind of shown in different ways. This one's a very basic one because we just have country for a column and population for a column. But you could also have, different descriptors along rows. Basically, you can make these as complicated or as simple as you really need to. You ever work retail and get a look at their profit and loss reports in a giant spreadsheet? Tends to hurt. What's really terrifying is how much of the financial world is resting on top of compatibility with old Word, Microsoft Excel documents. I literally worked at the criminal records unit, and there was a spreadsheet they used for all of the employees. And I asked a question about it, like, hey, this would be more efficient if it was this way. Well, the guy who made the spreadsheet doesn't work here anymore. Okay. So, yeah. If all of a sudden compatibility with old spreadsheets died, pretty much the entire country would collapse. Everything is resting on the shoulders of old Excel spreadsheets. So, our example table, I feel like we don't need too much of an introduction to tables, so jumping into the examples, we end up with all kinds of different questions. We have a bunch of different students. We have a bunch of scores based on different subjects. So this is one of those ones where you will have, stuff along the rows, stuff along the columns, and you just kind of move around to find out. So at the very least, for number 1, it's asking what was Sarah's average score. So average would be you add them all up and divide by how many you got, right? So Sarah's scores were 92, 78, and 95. So if we're trying to find an average for that, we take all of these, add them together, and then we just divide by how many we got. Finding an average is awesome, really quick. Unless you have way too many different pieces of data, then it isn't really quick. So we add them together, we get 265. Divide that by 3. And we get about 88 points. Doesn't matter how many threes you slap on that. I personally threw 3 of them on there. But that would be finding the average of one person's scores. And for the most part, you can kind of apply that to all of these. Who has the highest math score? You just look down the math column and find the largest number. Sarah at 92. What is the average English score for all the students? You take all your English scores. I don't think I need to jump over to the pen and paper right now. You'd add all the English scores together, 88, 95, 80, 89, and 85. Add them all together. I get 437, and you divide by how many different options we had, which was 5, and you get 87.4. You just add them all together, divide by how many you got. Yay, averages. We'll cover more of averages, I think next week. Oh yeah, we're not getting that far today. Okay. That's when you get into very basic statistics stuff for HSE and GED, and it's literally just mean, median, and mode. Mean is average. Median, middle one. Mode, most reoccurring. That is it. It's gonna be a quick one. So, number 4, who has the highest overall average across all subjects? That sounds kind of depressing to set up right now. What do you guys think? You guys understand averages? Kind of, sort of? Okay. Let's play around with that a little bit more. I'm gonna go ahead and do it. So, I'm looking for the averages. John has 85, 90, and 88. If I can get away. That. Oh my God, that broke. Effort. No. These ones you divide by 3, add them all together, divide by 3. Got 85, 90, 88. It's 264. That was pretty freaking close, right? Divided by 3, we get 88. Sarah, we already found in the last problem. It's 265 divided by 3. That one was 88 and a third. Mark, we had 76, 85, and 80. Cheap way to write it. That one's 241 over 3. Well, you definitely didn't get the highest score. What a failure, Mark. That is really small. Beat him for a month. All right. Said 88, 92, and 89. Pretty sure it's going to be close to 90. They're all close to 90. 88, 92, 89. That one's 269 over 3. We end up with about 89.667. So 89 and 2/3. Congratulations, you almost got an A. But you did. You're also a failure. So, all right. 90, 88, 85. That one ends up being 263 over 3. We end up with 87.667. So the highest overall grade in the class is the highest B in the class, who I said was still a failure. Such a shame. Such a shame. If a passing grade is considered to be 85 or above in each subject, how many students passed in all 3 subjects? Well, just all the ones that don't have anything in the 70s or below, right? You have to get 85 or better, so check. Nope. Sorry, Sarah's bad at science. How is Sarah that bad at science but that good at math? I don't know. Whatever. They're fake people. It doesn't matter. We could have named her Bert for all we know. Let's see. Mark, nope. 2 out of 3 are not passing. Lisa, congratulations, you're passing. And Alex, congratulations, you're passing. The only 2 passing. Cool. All right. 2 people pass, 3 people fail. Excellent. Imagine getting an 84 in all your classes and then just being told you failed. That wouldn't be cool. I wouldn't like that. The only way the problem could work though, because I mean, really, they all started at like, all their averages are like 80 to 90. So how many would have actually passed in the American school system? All of them. Just gotta lower the bar a little bit, then you get more people passing. All right, what is the range of scores for each subject? So a range of scores, you would just say, okay, what's the lowest to highest? With math, lowest would be 76, highest would be 92, so that's your range. Science, lowest is 78, highest is 92. Cool. And English, lowest is 80, highest is 95. Cool. Those are ranges. Do it make sense? It makes sense. Wunderbar. My God. Oh my God. Oh my God. Oh. I broke it. Actually kind of did. All right, fine. I didn't want to hit the button, but I had to hit the button. Cool. All right, so tables we can do. Next one we have would be circle graphs. Circle graphs are pie charts. You've seen pie charts, they exist. Difference between them and a table is everything in a circle graph has to add up to 100%. It's always based on percentages. You might not see a percentage. You might be given raw data for each of the sections in a pie chart, but it always has to add up to 100%. That way, each of the sections is kind of a good visual for what it is you're working with. And if you ever see a pie chart that is wildly inaccurate based on the sizes, whatever you're seeing that in, just completely ignore it as a source. That is trash. So here we have a survey of favorite pizza toppings. Conveniently enough, our chart is shaped like a pizza. Wow. This would be more entertaining if they had actually, color coded it based on red being pepperoni, yellow being cheese. That would be a lot more fun of a pie chart representing a pizza pie. But whatever. The main things here are that we have 4 sections. Write them down real quick. So the survey of 320 people was conducted on their favorite pizza toppings. How many people preferred supreme pizza? How many more preferred pepperoni pizza over cheese pizza? What percentage of people did not prefer pepperoni or sausage? All right, so question 1 is, how many people preferred supreme pizza? Well, we have that our supreme pizza was 10% of people. We have 320 people total. So the thing here is that since we're given just nothing but percentages, we can apply those percentages directly to 320 people, get some solid numbers, and roll with those. So you would take the 320, and remember we have a percentage. If we are trying to find the percentage of something, we will take that percentage, convert it to a decimal. So instead of 10%, we will have 0.10. Or you could always do 0.1. And we are going to multiply those two numbers together. So 10% of 320 would be 320 times 0.10. Do your multiplication, and you would end up with 32. That is how many people between our 4 options would prefer supreme pizza. Nobody's like, hey, what if I want to do like a nice, a nice Alfredo sauce and throw some chicken on there? Maybe some fire roasted tomatoes, That would work as a pizza. That always works as a pizza when I go to Papa Murphy's. But whatever. That place so expensive when you gotta take it home and cook it yourself. That's why I eat a Little Caesars, because my insides are garbage and I like my outsides that are going into my insides. I like those to be garbage too.
Well, Walmart chicken bakes are also pretty good.
Never had them. Never had them.
They're also over like $6 or $7.
It's not bad.
Yeah.
Might try that. I might just roll with Costco pizza because that's not even gonna lie, like 95% of why I have Costco membership is just to go in there and get pizzas. Like, hey, here's a pizza for $10. How big is it? Freaking gigantic. Right. How many more preferred pepperoni over cheese pizza? So the idea there would be we're looking for the difference between how many people preferred pepperoni and how many people prefer cheese. So the same thing we did for number 1, we would have to find for the pepperoni and cheese. Those are also going to be pretty quick options. 50% preferred pepperoni. So we have 320 multiplied onto 0.50. Half of 32 is 16. So half of 320 is gonna be 160. That's gonna be for pepperoni. Then we need cheese, 320 times it was 25%. So 0.25. You can do the multiplication, but it's also going to be 25%. If we just found 50, it's going to be half of that. You can just be cheap about it. What's half of 160? 80. And then how many more preferred pepperoni over cheese? You just subtract them. So 80 people preferred pepperoni more than cheese. Hooray. Good luck with the vegetarians, so I have to get used to cheese pizza. Here's the little Caesar pretzel pizza. Break or break. So we're great. Number 3. What percentage of people did not prefer pepperoni or sausage? That one's pretty easy because it's asking for a percentage. We don't need to get all these numbers here. We could just say, okay, we're starting at 100% and we're taking away the options of pepperoni or sausage. We can do those at the same time. Ahead of myself. So the sausage was 15%, pepperoni is 50%. So we're taking our 100, taking both of those off of there. You could do 100 minus 50 and then minus 15. You could do 100 minus, combine those, and you have 65. It really doesn't matter. As long as you put them together, you are good. Either way, you're going to end up with 35. And 35 what? Well, looking at it, that's the percentage of people that didn't like the others. Another option would have been to just ignore those two options altogether and add up the other two. Lots of options. I did it this way because if you had anything where it was really obscure and awkward and tiny numbers and a bunch of different percentages, and you're just looking for everything not included in a couple of different groups, then it's easy enough to just start at 100%, just cancel a few of them out. Questions on pie charts? I don't know about you guys, but personally, as the teacher, this is my least favorite lesson. Not gonna lie. Just because there's just a bunch of different types of charts, but they're all pretty basic, right? Tables, we've seen. Pie charts, we've seen. This one was kind of funky when I ran across it, but it's effectively just when you're making tally marks on things and then you cross the fifth one, just without crossing the fifth one. What you're kind of doing is making a bar chart, but you're just throwing data points above or throwing your count above those data points to be able to visually represent a count of some sort. For example, this one is saying cookies eaten at a party, 1x above the 6 means that one person ate 6 cookies at the party. And the number shows the number of cookies, so you can see, okay, how many people ate 1? 2 of them. How many had none? 1. How many at 3? You just count them. We get what, 8, 7? Going with 7. But it's a pretty basic concept, right? It's just making tally marks. The annoying part is actually arranging the data in a way that you can work with it. And speaking of annoying, I always hate myself for this particular problem. So what I did was I actually took all of these questions and applied them to one set of data. The downside, there's a lot of sets of data. So I have them all arranged. What I'm going to do is write out all my numbers. This would be a great problem for the statistics problems, but not for the line plot. Actually, just use the one from this example here. Oh. There we go, liney plotty. Isn't that beautiful? It's terrible. My God, it's terrible. Honestly, what would have been terrible is actually working with the numbers on that list. Number 1 asks, what is the most common amount of cookies eaten? And what is the least? That's not something we can really write down. It's just observing the graph, right? So if we look at this, we're just looking for the most common one, right? And that's just going to be the one that goes to the highest point. So the most common would be over here at 3, right? About as much size as I can squeeze out of that thing. So the most common would be 3 cookies, and the least common would be 0, right? One person decided to not eat cookies. I'm offended, you're offended. What's wrong with this person? You have 3 cookies in front of you, eat them. Well, I don't know, it depends on the party you go to. You gotta watch out. You never know. If it's a cult, definitely don't eat the cookies. If it's a children's birthday party, they're probably safe. But definitely don't eat weird snacks at a cult. Unless you're running the cult and you know what's in them. What is the average cookie count? Okay, so this would be like a real problem. Because this deals with averages, like the last chunk of information that we played with. But the problem is every one of these X's is just how many cookies they ate. But I'm going to show you a nice way of writing this. So if we're looking for the average of all of these, what we can do is we can say, okay, well, my data point at 0, I had one of those. Now, bear with me, I know that's kind of pointless, but, and then at my data point of 1, I had how many? 2. Okay, I could have just added 2, but there's a purpose to this. At my data point of 2, I had how many? 6? At 3, we had 7. At 4, we had 2. Five, we had 3. And 6, we had 1 guy. What is wrong with that guy? Why did he have 6 cookies? A lot of freaking cookies. So what I'm doing by doing this is I'm avoiding looking at my chart and saying, oh, if each of these people had 2, 2, 4, 6, 8, 10, 12, if each of these people had 3, 3, 6, 9, 12, etc. Because it's asking what's the average amount of cookies that people had. Every one of those data points is going to count as that many cookies. So we're looking at the total amount of cookies eaten over a party, and then we just divide by how many cookies we had. Well, I guess you wouldn't divide by how many cookies you had. It's going to be dividing by how many people you had, right? That's going to be the total amount of cookies. That's going to be the total amount of people. Well, how many people did we have? Well, at our data point of 0, we had 1. At 1, we had 2. At 2, we had 6, 7, 2, 3, and 1. So I'm just adding up how many were at each tick mark. You can kind of see that nice kind of pattern emerging. So I just kind of kept this as straight as I could in order to make that work out nicely for us. Downside is actually putting it all together. One times 2, that's 2, plus 2 times 6, plus 3 times 7, plus 4 times 2, plus 5 times 3, plus 6 times 1. We get 64 cookies were eaten. Across how many people? 1, 2, 6, 7, 2, and 3, and 1. About 22 people. Why did I just make that a G? All right. You know, my brain's a little fried. I don't know if I've had a fever or not, but something's going on up there, and I don't like it. So 6G, it's kind of the same thing when you stare at them. You know. So we divide these two, 64 divided by 22, probably something a little less than 3. Yep. Yeah, about 2.91 cookies per person. You know, I got cookies per person. I divided cookies by people. Cookies per people. That makes sense because you look at our chart, the highest point is 3, maybe a little. You know, the average you could expect to be a little bit to the left of that because so many were at 2. That makes sense. What else we got? What is the likelihood that a person at the party had 2 or 3 cookies? Now, if you think about how likely something is to happen, you might think a bunch of different things, but you might stumble across a percentage. Percentage would make sense, right? How likely are you to pull something off? 50-50, 60-40, you know, 60% sure, 50% sure. Percentage is a good way to go. So what we're gonna do is we're gonna play with a percentage, and we have 2 or 3 cookies. So we're gonna try to take that information and put it together into a percentage. So the question is, what do I do for that? Right? How do you get a percentage of one option or another option? Well, go back to an example of pizza. If I was selling pizzas, small, medium, and large, and I said, oh, an equal amount of people get each one, what's the likelihood of you getting either a small or a medium? Well, the likelihood of the small is 33%, and the medium is 33%, and you just add them together, right? One or the other, just add them together. So that's exactly what happens here. 2 or 3 cookies, we're gonna figure out the percentage for 2, we're gonna figure out the percentage of 3, we're just gonna add them together. Now, the nice thing is that a lot of that work we already did. Because if we're looking for a percentage, we would be going out of the total amount of people. Cool, we already have that. Our total amount of people is 22. This will be our 2 cookie people. This will be our 3 cookie people. How many people had 2 cookies? 6 of them. How many people had 3 cookies? 7 of them. Now, both of these, in order to get a percentage, you would say, oh, 6 out of 22, you would just do 6 divided by 22. That you would get 0.272727, blah, 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 forever, right? Now, convert that to a percentage, you move the decimal over twice. Kind of rounded there. I think that's pretty safe. We get 27.27%. That's not bad. Okay, what about the other one? 7 divided by 22. In this case, we get 0.3181818. Kind of see a pattern going there. For the love of God, answer her question. Yeah. So move the decimal over twice, we get 31 points. I did 2 decimals here, I'll do 2 decimals here. If I round it to those 2 decimals, it'd be 82%. But remember, I was deciding I was going to add them together to say, okay, well, this is the 2 cookie people, 3 cookie people. What's the likelihood you're one or the other? Just add them together. Now I could be really, really precise about this if I want to. Go to the calculator, go up to that guy, hit enter, pulls that in, add it to that, hit enter. And multiply that by 100 to get our percentage. That works. But it works. That gives you the same thing, 27.27 plus 31.82. Sure does. Reason for that is because I made sure I was accurate to those of that many digits. So anything I put together is going to be accurate to that many digits. In this case, we have 59.09. That's how likely you are to get one of those options. More than half the people. That makes sense. Free cookies. More than half of people are going to get a handful. One guy's like, yeah, I want 6. One person's like, I don't want any. I'm like, cool. We got enough for 3 for each of us. Mind if I take yours? Elaborate. But it would make sense. Line plots. Not bad, right? Now, applying them, I can make a mess out of that. You wouldn't expect that to be that messy. I just made those up at random. Let's just move on. We got bar graphs. I like bar graphs. You guys like bar graphs. Love them, right? Favorite thing in the world. You woke up this morning like, hope I get to see a bar graph. Well, dream has come true. We have bar graphs. So these are incredibly useful. They can be used to represent percentages. It can be used to represent frequencies. It can be used to represent any amount of data. And the nice thing is that, unlike a line plot, you could define your own scale. And by that, I mean, you look at the left-hand axis there, then for the number of people. Yeah, that's right now it's counting up by 1, but depending on the type of data you're working with, maybe it counts up by 10,000. Maybe you have 10,000, 20,000, 30,000. You're like, I'm not going to put a little hash mark on each and every one of those up to that point. You can count up by that. So you get to choose your own scale, whatever is appropriate for the data you're working with. Could be in millions, could be in billions, could be in percentages. Doesn't much matter. Good chunk of different data can actually be represented by a bar graph. So they're very, very useful. Here we have one along the side. So it's still bar graph, it's just going off in the other direction. So in this case, we have votes for favorite colors. It says how many votes were cast in this survey of favorite colors, how many more people voted for the most popular than the least popular, and what percentage voted for silver. So you can kind of look along this chart and very quickly gauge how many people voted for each one. I'm going to write those down real quick. Let's see, we got red, purple, blue, black, silver, and gold. So the nice thing is that for this one, it's scale along the bottom for the number of votes. Each one of these marks is another 3 on the scale. So for red, you can just go up to here, go down and say, okay, well, it looks like that was 33 votes for that one, right? Whereas for purple, purple goes a little bit past this one. Now, since each of these is divided into 3 marks, if it's a third of the way over, we're going to say it's 1. If it's 2/3 of the way over, like this guy, we're going to say that's another 2. So for purple, it starts at 21, goes 1 over it, so we're going to say 22. For blue, that one actually does just go out to the 21. Black hits the same point that purple does, so 22 there. Silver goes up to 9. And gold goes 2/3 of the way from 30 to 33, so that's going to be about 32, right? Those are the number of votes. In order to find the number of votes, that's easy enough. We just add them together, right? That's gonna be particularly useful for a lot of our applications with these numbers. Because then we can find percentages. We actually have a gauge on, okay, if there's, you know, this many people, based on these data points, we can guess how popular they really are. Let's see, add them together. 33, 22, 21, 22, 9, and 32, we get 139. That, our first answer. Not too bad. Just adding up all our data points. Now it says how many more people voted for the most popular color than for the least popular color. And yeah, we just wrote all those down, but you can immediately tell by glancing at the bar chart that red was the most popular color and silver was the least. So you would just find the difference between the two. You'd have 33 minus 9. I'm gonna write that on the page, but I'm not gonna switch over. 33 minus 9, you would just get 24. So that's 24 people. Even though we're referring to votes, it's specifically asking how many people voted. And it says what percentage of people voted for silver, that wonderful least favorite color. And for a percentage, you just take how many there were and divide it by what you got as a total. Silver was 9, our total was 139. 9 divided by 139. Zero 0.064748, blah, 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 forever. It'll just kind of keep going. Eventually it'll have to repeat, but I don't know how many decimals that would take. And that would be the decimal form of our percentage. Move that decimal over twice. We get 6.4748%. Love it. Are we happy? Not bad, right? Don't worry, I'm still saving the best for last. Two more types of graphs. So we have line graphs. These ones are pretty self-explanatory. They're usually over time. They're kind of showing trends. You look at a graph of stocks, you'd be like, wow, GameStop's useless. Out of a vague curiosity. Ah, cool.
Wasn't there like that whole thing a couple of years ago where it's just like,
Well, that was GameStop. This is my current company, Griffles. Ooh, there's their 5-year. Although I can tell you why plasma might have been in very high demand a couple of months into 2020, you know?
You look up National Guard products.
National Guard products?
Yeah, that's where I went. They don't have it.
No,
We spent a lot of money on some.
they're not publicly traded. Ah, look, GameStop had a good last hour. How are they at the 5-year? What the hell? Oh, hey, guess when all the bros decided to go crazy on GameStop stock?
Isn't that Modern Warfare? 2021?
I mean, there's Call of Duty every year, but that's when everybody started freaking out about GameStop stock because there was this whole thing where they actually made a movie about it. the rich, the GameStop saga? No. Dumb money. I got really, really tired of people coming in my store. So you get in on that stock thing? No, no, I don't. They don't pay us in stock. They don't pay us for anything. They put me in charge of a freaking plasma lab at my current job. And I'm like, the last guy quit because it was too much stress. I'm used to GameStop assistant manager work. Like, this is nothing. You guys are adorable. I could run this whole center and half pay attention. Never worked for GameStop. Retail PTSD is a thing. What was I talking about? Oh yeah, we have graphs. It's like graphs, right? No. Okay. I feel like that one's sarcasm. 2 out of 3 said no. 1 said yes. Would you like to guide the class in the next part of the lesson? No? What if I hand you a marker? Yes, I did connect all of these together when you guys weren't paying attention because that's how my brain works. If we had more, we could sort by them. Those are all of the markers. So, line graphs. Paying attention. Come on, ADHD. Got 2 more parts. Line graphs. They show how data changes over time, like the stock market. Figuring out how much your money is worth. It's going down. So the horizontal axis is almost always units of time because it makes most sense for us to keep track of data that way going left to right. It kind of hurts my brain if I was going top to bottom if I, on that direction. That would actually be kind of painful to work with. But you'll usually have what you're tracking along the left and time along the bottom. You can connect them by a line and estimate roughly, it'd be a linear estimate, but you could estimate at certain times a day, for instance. So here we have a line graph example. These are temperatures throughout a week. These are the high temperatures, so I take it it's either about to turn into winter or it's a standard Nevada week, which is all over the freaking place. So of the days shown, between which 2 consecutive days did the peak temperature decrease the most? So easiest way to tell would be, well, where is it steepest, right? Where does it drop off the highest? Where does it jump up the highest? Well, it only jumps up a couple of times, right? But between Monday and Tuesday, there's a pretty harsh drop off, right? So you would probably go with those options. So between Monday to Tuesday, that would be the largest of your decreases. Then it says between which 2 days was there the largest temperature increase? Well, those are only the ones, it's kind of nice to look at in these ones. The only time there's a temperature increase is where it's sloping upwards, right? So we can immediately ignore all of these parts. We can ignore this one. Literally just going to be this guy and this guy. And between these two, which one's the steepest going upwards would be this first one, right? So between Sunday and Monday. Then it says, what is the range from lowest to highest in temperatures recorded? So if it's asking for the range, you would either say, oh, between this one or and this one, right? So you would say, what's the lowest temperature recorded? And a lot of people would make the mistake of going with the low endpoint, but you have to go with the lowest overall recorded number here, which in this case would be halfway between 58 and 60, so 59, right? Then the highest point would be the highest peak in this entire thing, which would be 69. So even though it looks like a very dramatic change in temperature, this is only a scale bouncing between a total of 10 degrees. So overall, A pretty solid week, right? Not too bad. But that's a line graph. Any questions on those? Yeah, me neither. Okay, and my favorite, scatter plots. So scatter plots normally would have a lot more complicated applications, but for what it is we're doing with them at this point, they're actually not going to be too bad. Normally, you would have a bunch of different data points. Like it says here, they're comparing two different quantities using two axes, roughly resembling a standard XY graph, and it has a jumbled group of points. Usually these are relating, say, cost, values, that sort of thing. But you can generally see if there's a correlation between one piece of data and another piece of data. You have a giant mess of data points everywhere where it's not really giving you a particular shape, then they're not really correlating, right? But if you start plotting points and you notice that even though they're scattered, they're kind of following like a line or like a curve, then you can tell that there's a relationship. So all we're doing at this point with scatter plots is determining if they have a relationship between them, so if they're correlating to each other, and whether or not that is linear, nonlinear, positive, or negative. So really that just boils down to if your scatter plot kind of resembles a straight line, then it's a linear relationship. If it kind of resembles a curve, like it's not going into a straight line, but it's maybe turning into like a semicircle or curving in one way or another, then it's a nonlinear relationship. Reasonably, if it doesn't have a relationship, you would say none, no relationship. And then where it says positive correlation and negative correlation, it's basically just saying, okay, if it's positive correlation, that shape is going upwards. If it's a negative correlation, the shape is going downwards. As one thing is moving forward, the other thing is moving downward, right? So we just have a very quick example of a scatter plot. And just glancing at this one, you could say, okay, well, the numbers are all over the place, but it does kind of resemble a straight line, right? And because of that, you would say linear relationship. Are the values going up? Yes, they are. So it has a positive correlation. That is all we can really play with scatter plots at this point. When you get a little further, you can use these data points, and usually you use some type of computer-related math program or a fancy program and a graphing calculator, and you can get what's called the line of best fit, and you would calculate a straight line that best represents your data. It's very, very horrifyingly complicated to do on paper. I've never done it on paper. I never want to do it on paper. Big, it's ugly, it's scary. Don't do it. But that's how we work. So looking at our graph, is it the example of a linear, not linear, or is there no relationship? Pretty straight, right? Yeah, linear. Values going up or values going down? Up. Positive correlation. Cool. That's all we can really do at this point, but we can take this information, even though we don't have a line of best fit, we can kind of estimate what values we would have. Like if you're looking at this and you say, okay, you can kind of see a line along here. If you actually had a line of best fit, it would be crossing through those points in that shape. So number 3 and number 4 are asking for estimations at 21 degrees. So this was temperature versus sales. So apparently the warmer it is, the more sales this gets. Maybe it's, I don't know, maybe they're selling, maybe they're selling air conditioners. I don't know. Maybe they're selling, air salts instead of umbrellas. Maybe they're selling umbrellas when it's cold. I don't know. But at 21 degrees, we don't have a data point. That's between this 20 and 22. So if I picked a data point, it would have to be in this kind of region, right? Generally around here. So that would be midway between the 400 and 500. So you could probably guesstimate about 450, right? Hope good. You're transparent. Hope good you're transparent. I don't even care. Let's just get you off of the slider. There we go. That works. Doesn't look awful now when I click out of it. Good enough. All right. So you can kind of see it be at about 450. Then sales at 13 degrees. Well, at 12, it's just below 200. At 14, well, 14-ish, it's just above 200. So I bet if I needed to estimate, probably about 200, right? That'd seem about right. It could be, given that it's a scatter plot, things jump around a little bit. Could be as high as 250, you know? It could be a range. It could go lower. But just as a decent estimate, between these two is probably pretty safe. So about 200. Anywhere from 200, 180 to 250 would probably be pretty acceptable. Does that make sense? Yeah. Because otherwise, all you can really do is estimate. You'd actually be able to take a couple of these points and with the next lesson, draw a graph between them. And, you know, it might not be the line of best fit, but it might be a good estimation. And then work with that for your estimations. That would work fine. But yeah, that's the end of our charts and tables and graphs and what have you. So I got nothing else past that I can cover in the next 15 minutes. You guys to call it good, happy to call it good there? Yeah. All right.